Hello. All right, we're live. Hi, everybody. Thank you for bearing with us. We'll get started right now. As usual, if you have an idea for a future coffee shop talk, please visit our website and fill out our Google form. If you happen to be in the Madison area on February 17th, our colleagues in Madison are doing an Astronomy on Tap talk. One is Heated Rivalry Space Edition and the ninth planet of the solar system, Why Pluto Had to Die. Now, who are we? We are a group of postdocs and grad students at the Leonard E. Parker Center for Gravitation and Cosmology at UWM, and we give these talks every month here at Anodyne. And today's speakers are myself, sadly I'm not visible, Amanda Baylor, and Ronan Humphrey. And today's talk is called Love Written in the Stars. So if we zoom out and look at our galaxy, the Milky Way, we have it's roughly 100,000 light years wide, where 1 light year is about 5 trillion miles wide. It's roughly 1,000 light years thick, and inside there are over 100 billion stars. And if we zoom into our solar system, we only have 1 star and 8 planets. Sorry, Pluto. But a lot of stars don't go it alone. A lot of stars exist in binaries. Roughly 1/3 to half of all the star systems in the Milky Way are in binaries. At least half of sun-like stars, that means stars that are roughly the same mass as our sun, have companions. And companion likelihood goes up with mass. And that just means as we look at more and more massive stars, the likelihood they have a companion increases. When we get to stars that are about 16 to 20 times the mass of our sun, the likelihood they have a companion goes up to about 80%. But today, what brings us together, marriage is what brings us together. The marriage of these stars is what brings us together, and what brings stars together is gravity. Binary stars are defined as 2 gravitationally bound stars that are orbiting a shared center of mass. There are a bunch of parameters that astronomers use to categorize these orbits that help us better understand how they behave. The first one is orbital period. That's how long it takes to complete 1 revolution. Another is eccentricity, and that basically means how ovally is the orbit, or how much does it deviate from a perfect circle. So here we have an example of a perfectly circular orbit and an elliptical orbit. And the way that we put a number to eccentricity is basically if we start at eccentricity of 0, we have a perfect circle. And as we increase, it's more and more ovally until we get to an eccentricity of 1, where now we have a parabolic orbit, and that's actually unbound. So if something were in a parabolic orbit, it would kind of go past and then keep going completely away. Another parameter we have is apoapsis. This is the farthest point in the orbit from the center of mass. So we have our center of mass here, and for each of these 2 stars we have here, their apoapsis is all the way out here. Another one is periapsis. This is the closest point in the orbit that the stars pass to their center of mass. In this case, for each of these stars, it's roughly here and here. Now, some of these binary stars are closer than others. In close binaries, they're very close in proximity. They evolve together. They can even have mass transfer. And they usually have relatively short orbital periods on the order to hours or days. Down here, we have an example of W Ursa Majoris. This is a binary that's in an orbit that takes only 8.5 hours. And these 2 stars are about 1 million miles apart. Now, I know it looks in this image like they're actually touching, but what we're actually seeing here is their outer layers of atmosphere that are touching, and you're going to hear a little bit more about what that means later in the talk. We can also have very wide binaries that are very far apart. These stars tend to evolve independently, and they don't experience mass transfer. They can also have super long orbital periods on the order of hundreds of thousands of years. The Alpha Centauri system, which is actually a triple system, consists of Alpha Centauri A and B, which are pretty close together in a close orbit, but also they're in a larger orbit with the star Proxima Centauri, which is the closest star actually to our star. They're in an orbit that lasts about 550,000 years, and they're about 1 trillion miles apart from each other. Now, the way that we know things are in a binary depends on how we look at them. So if we have something called a visual binary, this is when two stars are close enough in the sky that we can tell that they're in an orbit, but we can also see that they are actually two stars. So an example here, this is Alcor and Mizar. This is a visual binary that is in the Big Dipper constellation, which you can kind of see here. But actually, if we look a little bit closer, it gets more complicated. If we take a telescope and we look a little bit closer at these two stars, we'll actually see they're not two stars at all. They're actually 6 stars. None of these are actually a single star. So Alcor over here is a binary with a larger main sequence star and then a red dwarf star. And Mizar is not even one binary, it's 2 binaries that are orbiting each other. All 6 of these stars are gravitationally bound in something called a hexary. Now, some of the most powerful optical telescopes in the world still can't resolve some objects as 2 shapes. Let's go back and make sure we get that picture up. So a telescope's resolution is basically how close can 2 objects be, and the telescope can still tell that they are 2 objects. So here we have 2 objects that are close together, but not so close that they can't be resolved, so we see them as 2 objects. If we have 2 objects that are just right at this, the angular resolution of the telescope, they kind of look like an extended source, so you can kind of tell it might not quite be one source, but you can't quite definitively tell if it's 2. And if they're too close together, it just looks like one very bright source. So if you remember Alcor and Mizar, they were close enough together that the angular resolution of our eyes is not strong enough to be able to tell that Alcor is 1 binary and Mizar is 2 binaries. So we need to look at variations in their light to be able to tell what we're looking at is a binary. And one way we do that is through something called Doppler shift. Now, the most common example you might have heard of about Doppler shift is an ambulance. So whenever an ambulance is coming towards you and its siren is going off, it appears to have a higher pitch when it's coming towards you, but as it's going away, the pitch gets lower, and it has a lower frequency. This can also be applied to light. If we look at our handy-dandy electromagnetic spectrum, if we have light that is redshifted, it appears to be at a lower frequency and longer wavelength, and if it's blue shifted, go back. If it's blue shifted, it appears to be at a higher frequency and shorter wavelength. So in spectroscopic binaries, these are binaries that we're able to identify by the changes in wavelength we observe in their spectral lines. So whenever the primary star that we're observing is coming towards us, the light appears to be blue shifted, so its wavelength will appear shorter, its frequency will appear higher, but then when it's in the part of its orbit where it's starting to travel away from us, it appears to be red shifted. So so the wavelengths we observe appear to be at longer and at lower frequencies. Another way we can also tell if something is in a binary is seeing if it's eclipsing. And the way that we see that is the apparent brightness that we see from the star gets changed. Here we have an example of the star Algol, which is part of Medusa's head in the Perseus constellation. And whenever one star in the binary passes behind another, there's a bit of a long dip in the brightness. Then when they're both visible, it's back at normal. And then when the other star passes behind the companion, it also dips again. So very recently, you might have heard in the news about the star Betelgeuse. It's one of the brightest stars in our sky. And it was recently discovered to have a companion star in a 6-year orbit. Now this companion star is really, really, really tiny compared to the actual size of Betelgeuse. So the only way that we can tell that it's there is how it affects Betelgeuse's stellar atmosphere. So this is an artist representation of the Betelgeuse and its companion. The companion is actually not to scale. It would basically look like a single black pixel on this. And it's actually so close to Betelgeuse that it passes through Betelgeuse's stellar atmosphere, and it causes this wake of gas particles to go in front of Betelgeuse whenever it's eclipsing it. And this wake of gas particles, you can kind of think of it like ripples in water whenever a boat goes through it. It gets disturbed, and it affects how we see the water, or in this case, the gas particles from Betelgeuse. So what this looks like in data is that this wake of particles creates a brightness effect that we see whenever whenever the companion star is in front of Betelgeuse. So this first peak is the brightness that we observe from Betelgeuse when its companion star is in front of it. And this brightness that we see is caused by that wake of particles. And this blue line represents the brightness we observe when the companion star is behind Betelgeuse and we can no longer see that wake of gas particles. So now, we've talked about binaries, we've talked about how we know things are binaries, but now we want to talk about how do they meet up? How do they become binaries? And we're going to start with talking about stellar nurseries. The interstellar medium, that is the space between stars in our galaxy, is not empty. It contains a lot of gas clouds, and inside these gas clouds can be clumps of gas that come together closer and closer as the force of gravity brings them together. And eventually, they form these little star-forming regions. This is a picture of the pillars of creation that was taken by the JWST telescope. And these little red regions here represent star-forming regions. In these molecular clouds, eventually you start to form these gas clumps that start to attract more and more and more material until eventually they become so massive that the gas pressure that was holding up the molecular cloud is no longer able to support it, and it gravitationally collapses into a baby star. And we call these baby stars protostars. There's a bit of a delay between when I click it and when you guys see it. So this is an example of a protostar called HL Tauri that was observed by ALMA. And in the middle here, we have this core that's the collapsed cloud that has now turned into a protostar. And this collapsed protostar can still draw in material from the molecular cloud and form this protoplanetary disk. And all of these lines that you see going outward, these are areas where we think new planets are forming. Now in this case, we have just one protostar forming, but that doesn't always happen. You can also have, sometimes during the gravitational collapse, the cloud can fragment, and now we have two protostars forming a brand new protobinary. And with that, I will hand it over to Ronan.
All right, so I'm going to talk about some toxic relationships. And first, I'll give a brief, hopefully, review of stellar evolution. If you've been to one of our talks before, you've seen a slide like this. This is the stellar evolution chart for an isolated star, so a star that is by itself. On the top branch, we have stars that are lower to intermediate mass, so stars like our sun. They spend most of their lives as main sequence stars, where they are burning hydrogen, turning it into helium. And then as they start to use up their hydrogen and more helium is building up in their cores, they will expand into what's called a red giant. They will continue to burn hydrogen on their outer portions, and eventually they will start to burn some of their helium into some heavier elements like carbon and oxygen. And as that starts to happen, they start blowing off the outer layers in what's called a planetary nebula. And then we end up with the core of that star, which is now a carbon and oxygen core, and it no longer undergoes nuclear burning. So it's kind of a dead star. And then on the bottom, we have the evolution for higher mass stars. They turn into red supergiants after they exhaust their fuel. And then they keep fusing heavier and heavier elements all the way up until iron, at which point they can't get any more energy out from fusion, and they will collapse and then bounce back in an explosion called a supernova, and we'll end up with a black hole or a neutron star. Now, binary stellar evolution is much more complicated. So we have all of these branches here, and it's still separated by mass. So in this green section all the way on the right, this is for wide binaries, so stars that are too far apart to really interact with each other, and they'll just basically evolve by themselves as they would if they were isolated stars. And then in this yellow section, we have all the different outcomes for lower mass binaries, and then in this blue section, we have the higher mass binaries, and you can see this leads to a very diverse set of outcomes. I won't be able to cover all of these, so I'll just focus on this branch here. There we go. So we start with our binary stars orbiting their shared center of mass, like Lulu showed us. We define this region called a Roche lobe, which is an imaginary region around each star, wherein all the gas in that region is gravitationally bound to that star. So all the gas in this region will be bound to that star, all the gas in that region will be bound to that star. And there's one point called the L1 Lagrange point that is sort of shared between those two Roche lobes. So gas on that point can flow between the two stars. The clicker is really throwing us for a loop. There we go. Okay, so there's three basically different scenarios for this. The first is a detached binary wherein neither star has filled its Roche lobe. So all the gas for this star will stay with this star, all the gas for the other star will stay with the other star. And then we have semi-detached binaries wherein one star has filled its Roche lobe. And what that means is that material from the star that's filled its Roche lobe can fall through that L1 point and into the gravitational pull of the other star. The clicker, man. You're getting so many spoilers. All right, and then we have contact binaries. And these are binaries wherein both stars have completely filled their Roche lobes and they're sharing their outer layers of material. Come on. All right, so one example of these are these kissing stars. This is VFTS 352. This is a binary system. I have an artist interpretation on the top right there. This system is in the Tarantula Nebula, pictured on the bottom there. These are both very large, very hot stars. They're about 29 times the mass of our sun, each of them, and they're tidally locked together. So that L1 point where they're kissing always stays facing each other, and that's what they're rotating around. And we don't know the final fate for these stars. They could either merge and become one rapidly rotating star, or they may both die supernova and then become a binary black hole system. What is up with the slides? All right, so cataclysmic variable stars are an example of a semi-detached binary. And these involve a white dwarf star, so that dead carbon and oxygen core of a star, and a sort of regular main sequence or red giant star. And usually it's a red giant star, is filling its Roche lobe, and so material is falling through that L1 point and falling towards the white dwarf. And because they're rotating around each other, that material will settle in what's called an accretion disk around the white dwarf. And these are called variable stars because as that material falls in and rotates around, it gets heated up, and so we see a change in brightness over time in these stars. Come on. All right, so these are formed in a very specific way. So you start with a binary of two main sequence stars orbiting each other. The more massive one will use up its hydrogen fuel first and will become a red giant. All right, so that will start expanding and it will overfill its Roche lobe as it expands. We're just gonna do spoilers. So we look at the one on the right. So it starts to overfill its Roche lobe, and it'll start falling onto that other main sequence star. Eventually, it will expand enough that it fully engulfs the other star in what's called a common envelope because they're sharing those outer hydrogen layers. The core of the red giant, which is what's here, will rotate around the main sequence star in that common envelope, and they'll actually blow off that fluffy hydrogen layer that they're sharing, and we'll be left with a main sequence star and a white dwarf. And then that main sequence star expands into a red giant, overfills its Roche lobe, and will start transferring mass onto that white dwarf, and we'll get that accretion disk like you saw in the previous figure. And these systems can explode in what's called a nova. Nova is Latin for new, because what these look like in the sky is a new star appearing. So what happens is as the hydrogen falls in, it falls through that accretion disk and starts accumulating on the surface of that white dwarf. It gets heated up and gets put under more pressure as more gas piles on top of it, which eventually starts hydrogen fusion right on the surface of that white dwarf. So that basically explodes out and gas is ejected at millions of miles per hour. This is an artist's representation on the right of what that might look like. And this causes a short, bright burst of light, about 100,000 times brighter than our sun. And this brightening will last for days to months. And we see about 5 to 10 of these in the Milky Way galaxy each year. One example of a nova is Nova Centauri 2013, also called V1369 Centauri. This was actually discovered by an amateur astronomer, John Seach, in Australia on December 2nd, 2013. A lot of these are first seen by amateur astronomers because they're really bright, and we don't know when they're going to happen. So if you're just looking out every night, you might see a brand new star, and that might be a nova. This system reached peak brightness on December 14th, 2013. So what that looked like is, if we go from the panel on the left, that's its quiescent state. So when not a lot is happening and just mass is accumulating in that accretion disk and on the white dwarf. And then there was a dwarf nova, which is some of that brightening from just the gas heating up as it falls in and there's some friction forces. And then the third panel is the nova eruption. You can see it gets much brighter and almost appears bigger, but that's just because it's brighter. And then it will dim and go back to what it looked like before. So both stars are still there afterwards, they've just lost that gas that was ejected. And this system in our sky was actually as bright as the Andromeda Galaxy is to us, so this was quite bright. And this system was also the first time we found lithium in the ejecta from a nova, which supports the theory that younger stars have more metals because of novae happening in the area where they're born before they're born. Right. Now I'll talk about some fatal attraction. So first example is the Black Widow pulsar. So a pulsar is a rapidly spinning neutron star, so one of those massive dead stars. This particular one is pulsar B1957 plus 20, and it has a brown dwarf companion. So a brown dwarf is basically a failed star. It's bigger than any planet would be, but it's not quite big enough to start hydrogen fusion, and so we don't consider it like a real star. And this teeny tiny brown dwarf companion is being destroyed by high energy winds coming off of the pulsar. And then because the pulsar is spinning, it has these beams of light from either pole that Amanda's going to tell us a little bit more about later. And astronomers really like this system because as those beams pass through the gas that's being blown off the brown dwarf, it amplifies the beams and helps us see it better. Another example of fatal attraction is type 1a supernovae. These are a kind of supernova that occur in binary star systems that have a white dwarf. They're about 5 billion times brighter than the sun. I have supernova 1994D on the bottom right here. Let's see if I can get my arrow. Nope. All right, there it is. And it's in the galaxy NGC 4526. And as you can see, when it erupts, it is brighter than its whole galaxy. Unlike novae, the white dwarf is completely destroyed in this explosion, and so it doesn't return back and nova again. This only happened once. And astronomers really like these because they can be used as standard candles to measure distances. And if you come to our talk next month, you'll hear a lot more about them. We're getting so many spoilers. All right, so how these happen is the white dwarf will gain mass from its companion. This can either be from that Roche lobe overfill, like we saw in the cataclysmic variables, or it could be with mergers with another white dwarf. So as mass accumulates on the white dwarf and it gains mass, it will increase in temperature and pressure within the white dwarf from the gravity pushing down on it. and that will reignite nuclear fusion. So the white dwarf is made up of carbon. The carbon will start fusing, and that will release more energy. Now, in a normal star, the release of energy when it undergoes fusion will cause the star to expand, and then it'll kind of cool, and then the fusion will reduce. But in a white dwarf, they're not able to respond to temperature like that because they're held up by what's called electron degeneracy pressure, which doesn't depend on temperature. So as the temperature increases and fusion starts happening, that releases more energy, causes the temperature to increase, but it has no way of cooling itself. So this will cause a runaway thermonuclear reaction, and the entire white dwarf will be completely destroyed. So my animation wasn't good enough, so I'll show you one that NASA did. So here's an example of a supernova 1A that is from mass accretion by Roche-Loeb overfill. You can see that it's this huge, bright explosion, and then the white dwarf is completely destroyed at the end, and the companion may be destroyed, or it may be launched out into space at incredible velocities. And during these explosions, we get more heavy elements than were there in the beginning. So I'll highlight some here, if it'll let me. There we go. One of them is the calcium in our bones, and the other is iron in our blood that our hearts are pumping. And to get the rest of these elements, I'm going to turn it over to Amanda to tell you how we get those.
Okay, so everybody can hear me, I hope. All right, so now I'm going to tell you about matrimony. So we have stars that have gotten together, they've been dating for a while, they've been either killing each other or living in happily wedded bliss, but I'll tell you a little bit more about that in my section. So stars can merge. Let me see if I can get there we go. Okay, so stars don't really have high standards for finding partners. Stars are not very picky. They can get together with any other star, regardless of its mass, its size, where it is in its stellar evolutionary track, and if it's hot or not. So stars don't really care if you look good, they'll still match with you. And any star in the universe can collide with any other. They can rip each other apart, they can collide head on, but it really depends on where they grew up and who they know in their neighborhood, kind of like how we date. So they are either like dynamically interacting with another star somehow and getting captured and then colliding, or they've already been in a binary for a while and they just decide, okay, it's time to merge and collide. And in case you were worried, a collision involving our own sun is actually not very likely because we're not near any of these dynamic or stellar star-forming regions. So our sun is likely to be single and alone forever, just a single parent to us here on Earth, basically. So Ronan showed us this earlier, the stellar evolution diagram, and I'm going to focus just on when the stars have reached the end of their life, here at the end, where they've formed black holes and neutron stars. So as a reminder, a pulsar is a rotating neutron star, so I'm going to talk about these first. And neutron stars are just the remnants of these dead stars. They're extremely dense and packed with neutrons. And with a pulsar, it's emitting these beams of radiation at regular intervals. It kind of looks like the light of a lighthouse. And whenever that light shines towards us, we can detect it here on Earth. And it's kind of like the heartbeat of the star because these are really, really regular signals. They're either milliseconds apart or seconds apart, but they kind of act like clocks. So they're very regular and we can predict them really well. And they can also be in a binary with another pulsar or any other companion. Remember, they're not picky, so they could be with a white dwarf, another pulsar, another neutron star that's not pulsating. It doesn't really matter. So of course, I have to talk about what is essentially the celebrity couple of binaries. This is the Hulse-Taylor binary. So this is a binary that was discovered by Hulse and Taylor in 1974. This is a binary of a neutron star and a pulsar. Remember, every pulsar is a neutron star, but not every neutron star is a pulsar. So one of them is emitting these beams of radiation, while the other one, let me see if I can get the pointer up. Yeah, so one of them is emitting a beam of radiation, while the other one is not. And they saw that the pulse arrival times varied due to the presence of the companion. So the pulses were actually arriving sooner when it was moving faster in its orbit with its companion, kind of like a Doppler shift. And then when it's moving slower in its orbit with its companion, then the pulses arrived farther apart. So they discovered that this was actually in a binary. And this won the Nobel Prize in 1993 for the discovery of a new type of pulsar. But it's important for several reasons, not just that it's a new type. So it confirmed the existence of neutron star binaries. You know, we knew neutron stars existed before, but this was the first time that we had actually observed one in a binary with another one. It's also important because since it is in a binary, we are able to measure the masses really effectively. Like Lulu explained to us earlier, we can measure masses of the companions. And we don't really know what like the maximum and minimum mass of a neutron star is, so it's really important to have as many measurements as possible. And then also, it's good evidence for gravitational waves. And this was the first time we were actually able to prove that gravitational waves were real and that predicted by Einstein, they were proven here. So they saw that the orbit was actually shrinking slightly as they orbited. They actually get closer together every time they make one revolution around by about 3.1 millimeters. So they're getting closer and closer together, and eventually they will merge. But they found that the reason it was sort of getting closer and closer together is not because they're like, you know, super attracted to each other or anything, although they probably are, you know. But really the reason is they're losing energy in the form of gravitational waves. So I'm going to tell you a little bit about that next. So gravitational waves can be produced by neutron star binaries merging. So as neutron stars in a binary lose energy, they get closer and closer together and they emit these waves. And gravitational waves are essentially just ripples in the fabric of space-time, and they propagate outward from their source, kind of like ripples on a pond. And neutron stars are extremely dense. They're deforming the fabric of space-time as they move around. And these mergers cause really loud signals of gravitational waves, which we've actually detected directly in the case of GW 17817. That was a binary neutron star merger that's extremely important for astrophysics today. So I can't talk about binary neutron star mergers on Valentine's Day without talking about the love numbers. This is not a joke, this is for real. This guy named Augustus Edward Huff Love, he was a mathematician who introduced love numbers in 1909. He introduced the love numbers H, K, and L. And what they are these dimensionless numbers, so that means they don't have any units on them, they're just pure numbers. And they describe the rigidity of a body under the influence of tidal forces. So what does that mean? So imagine you have a ball, like the disco ball, for example, that's hanging from the ceiling. So that describes how squishy the ball is or how rigid the ball is. So a higher love number indicates an object that is squishier or more elastic, like a bouncy ball, and a more rigid body, like a disco ball, has a love number of H, K, and L all equal to 0. So it's completely rigid. It won't be under the influence of any tidal forces if something was acting on it. Now, he actually wanted to study the effect of Earth's tides on the surface of Earth, like how much Earth was actually being deformed due to its tides and due to the influence of the sun and the moon. So that's the original reason that Love introduced these numbers. But they are applicable to gravitational waves. So when detecting gravitational waves, we measure this thing called the tidal deformability. That's this lambda over here on the left. So when we detect gravitational waves, they look like this. This is the gravitational waveform. In black, I show the waveform as it's undisturbed with no tidal interactions at all. So neutron stars are squishy, so they can be squashed by their companion, kind of like here at the bottom. And when that happens, the gravitational wave signal actually arrives sooner as opposed to if it didn't have any tidal influence from its companion. So in the blue, you can see that it actually merges faster than it would if it was not under the influence of any tidal forces. So if we detect gravitational waves from a binary neutron star merger, this allows us to calculate the object's love number, K. And K specifically describes the influence of the companion on the other neutron star and how it's being squished as they in-spiral. And this is really important because we can't recreate neutron stars in a lab, so we want to be able to measure exactly what's going on inside of a neutron star. So they think that neutron stars have a love number between 0.05 and 0.17. Remember, we only have like one data point, so it's kind of hard to measure this number. So that's why it's important to keep getting gravitational wave detections. But we think that neutron stars are actually pretty rigid objects. I should mention also the radius of the stars in this equation, which we can also get from gravitational wave measurements and other methods. But it's a really simple equation. So as soon as we have the neutron star merger, we have the tidal deformability, the radius, and the love number, then we can figure out the love number K. I should also give a shout out to black holes. Sorry, I had to go back. Black holes have a love number of 0, so they're actually really rigid objects, and they're not deformed by their companion like neutron stars are. So it is a very explosive romance with these two stars. So neutron star mergers create these highly energetic explosions called kilonovae. And they're called kilonovae because they're 1,000 times brighter than those nova events that Ronan was talking about earlier. And they're visible for weeks to months after the merger. The neutron stars collide, they create this big explosion, and then there's an afterglow remnant radiation that we can still see later on for weeks or up to months. And in this explosion, a lot of stuff gets thrown around, like neutrons and different heavy nuclei. And that sets in motion a process called rapid neutron capture, which I'm going to tell you about next. So rapid neutron capture, or R process as it's commonly called, specifically happens during high energy astrophysical events like neutron star mergers. What happens is you have all these nuclei and these neutrons floating around after this explosion, and they have so much energy that they are colliding into each other. So neutrons end up bombarding the original element nuclei, and then the nuclei have captured these neutrons, hence the word capture in the name. And eventually those neutrons decay by releasing an electron, and that turns them into a proton. So this ends up fusing really heavy elements, heavier than iron. Iron's kind of like the end of life for a star. Once it fuses iron, it's pretty much done. So we need to get these heavy nuclei from these neutron star mergers. And this happens really, really fast. The nuclei then decay into stable isotopes, which just means that it has the correct number of protons to be that element, but it might have a different number of neutrons, like more or less. And that's what an isotope is. Okay? So this is the periodic table with showing the merging neutron star elements in the bright yellow. So Ronan talked earlier about the stuff in blue, but I'm just going to specifically talk about the merging neutron star things. And actually, merging neutron stars account for over half of the heavy nuclei, heavier than iron. So merging neutron stars are really important to generate these elements. And specifically, I want to point out two right here. That's platinum and gold, which we use to make our lovely wedding rings that we use to show our love. So thanks, neutron stars. That's very nice. Okay. Now, neutron stars actually take a really, really long time to merge. This process does not happen that quickly over time. When they do get pretty close together, the merger happens really fast, but it takes them a while. So they're doing this cosmic dance for a long time. So sorry it took me so long to ask, but will you merge with me? One star proposes to another. And if I can get it to work. Oh yeah, OMG, yes, I thought you would never ask. So basically, gravitational radiation is very, very inefficient. The energy lost by gravitation waves takes a really, really long time. And actually, most neutron stars will not merge within the age of the universe. So it's going to take an extremely long time for them to actually meet and get together. And when they do get together, it's a really special and rare occasion. Okay? So now they go through this thing called the honeymoon phase. So our neutron stars have merged, they've been just married, and now, this is going to be complicated with the animations. If the neutron star remnant that is left over after they've merged is less massive, then it will hopefully maintain a stable neutron star. If it's too massive, above about 2.2 solar masses, this is what we think the limit is about for neutron stars, it will just collapse promptly into a black hole. And if it's still too massive and unstable, it'll collapse. It'll stay alive for a couple seconds, but then collapse into a black hole anyway. And it will collapse on slower timescales if it's still a little less massive than the limit. But at the end of the day, if it is less massive and stable, then it will maintain a rotating neutron star just for the rest of existence. So it's not exactly till death do us part, because these neutron stars and black holes can go on to merge again. And we have more examples of this with gravitational waves. We've detected gravitational waves from neutron star black hole binary mergers and from black hole binary mergers. So we know these things continue to merge. And there is no divorce court for neutron stars or black holes. Once they merge, you cannot separate them. So they're going to be together for a long time. And we do have evidence of like stellar mass black holes merging, like 30 times the mass of our sun about. But we also think that supermassive black holes can merge in the centers of galaxies when they collide. But it's more like together for eternity, because isolated neutron stars can live for billions of years, like the age of the universe. Black holes also can live, if they're around a stellar mass black hole, 10 to the 67 years, and up to 10 to the 100 years for supermassive black holes. So for scale, the age of the universe is only 1.4 times 10 to the 10. So that's a 1 with 10 zeros after it. That's 14 billion years. So black holes will probably be the last things to exist when the universe ends, because it's just going to take such an absurd amount of time for them to evaporate and go away. So they will be together for a long time. And in fact, our universe will probably just die in a heat death where all the stars burn out and all of the black holes are just left hanging out in empty space. And the pair will remain together until they just fade into the darkness as neutron stars or evaporate into nothingness as black holes. And their union will endure through the end of the universe. Oh, so sweet. Love it. Okay, so in conclusion, binary stars are responsible for some of the most interesting phenomena in the universe. So they're really common, a lot more common than you would think. When you look up into the night sky, you might see a star and think, oh, okay, it's just one, but actually it's probably two. Binary star systems also allow us to measure properties that we're not able to recreate in a lab, where we have extreme states of matter, like the mergers of neutron stars or black holes. And then they're also responsible for a lot of the elements that matter to us in the universe. Novae, type 1a supernovae, kilonovae enrich the universe with these heavy metals that we're not able to get otherwise. So that stuff that goes into our blood keeps our hearts pumping, the calcium in our bones, and the rings we wear on our finger. So it's nice that we get to live and breathe and love each other thanks to binary star systems. So thank you so much for listening, and we'll be back on March 7th for building a measuring tape for the universe.